Hi, I'm your tutor Starla, and I just want to describe to you how to use the Polariscope correctly, because I've had some people that, have put the stone in the wrong place and can't quite get the results. So today, it's the Polariscope. The reason the piece of equipment is called the Polariscope is because it has Polaroid plates that are used to analyze light. Polaroid plates are very simple. They're really just a piece of glass or plastic that's been impregnated, usually with iodine crystals that have been oriented so they all follow the same direction. So when you have a Polaroid glass, really what you have is a series of lines going across your lens. Why does this work? Well, we know that light vibrates in all directions and it travels out from a source. So it's vibrating in all the directions and it hits your Polaroid glasses, and only the wavelengths that are vibrating parallel to the spaces in your glasses will pass through to your eye. All these other wavelengths get absorbed by the iodine crystals, and that's why they appear dark, because they've absorbed all of these other wavelengths and only allowed the wavelengths that are traveling parallel to go to your eye. This light that reaches your eye is called polarized light. It's light that only is vibrating in one direction. So a Polariscope actually has two Polaroid plates. This is what the Gem A Polariscope looks like, and this is another type of Polariscope that's used throughout the world. The Gem A Polariscope is a really nice portable piece of equipment. To open it, you flip down the bottom piece and continue around. Then you take the center piece, it comes out of the hole through the back, and you flip it around and it creates a C. You have a Polaroid plate on the bottom and a Polaroid plate on the top. This is the same piece of equipment, it's just stationary, and it has a light source on the bottom. It has a Polaroid plate that's fixed on the bottom and a plate on the top that you can actually turn. The bottom plate's called the polarizer and the top plate is called the analyzer. What you do is the plates will be lined up initially perhaps in the open position, and what that means is that the bottom Polaroid plate has the filters lined up in this direction, and the top Polaroid plate will also have the lines lined up in the same direction. If they're parallel like this, the Polaroid light will pass through and you'll see light coming through the top of your Polariscope. But if you cross them, one vibrating in one direction and one vibrating in the other, called cross polars, no light will transmit through your Polariscope. And I demonstrate this with this light source. I turn on my light, my mag light, and I put a Polaroid plate in front of it. You should be able to see light coming out of it. However, if I take another Polaroid plate and put it in front of it, if the polars are crossed, no light comes through. If the polars are open, you can still see the light. So we perform the Polariscope in what we call the cross-polar positions, where no light is transmitting through the Polariscope. The Gem A Polariscope already comes with the polars crossed. One filter has light going through in this direction and the other filter is crossed, so all light is blocked. You have a light source that it's the little flat piece. You put your Polariscope on top of the light source. You look through the top and you shouldn't see any light coming through it. You take your gemstone and you place it on the inside between the two polars, and you turn your stone in a circle. Two things can happen. If the stone is doubly refractive, which means it breaks light into two different wavelengths, each vibrating in different directions, what will happen in a doubly refractive stone is the light will come out through the bottom polar and hit the stone, and the stone will break the light into two wavelengths. One of those wavelengths will be vibrating in one direction and one in another, and at some point that other direction, the wavelengths will be vibrating in the plane that the top filter is adjusted to, and it will show light through the top of the Polariscope. So when I turn the stone in a circle, it may go dark and light and dark and light, where that wavelength that's being transmitted will either be in the correct direction of the analyzer on top or in the opposite direction, so it absorbs everything. So if you turn your stone really fast, it'll go blink, 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 light, dark, light, dark, light, dark, light. But if you turn it slowly, what you'll actually see is that there's a dark brush that sweeps across the stone. The darkness sweeps across the stone. And it's usually just one big brush. So quickly, that will just be a light and dark situation. But slowly, you get this lovely brush. And if you look in your handbook, you'll see this diagram of the different results that can happen. In a singly refractive stone, because it doesn't change the light, it doesn't separate it into two wavelengths, you never get the light and dark. The stone just stays all light or all dark. But in a doubly refractive stone, you're going to get the blink. Now, if you like to do something for fun, there's another thing that you can do with your Polariscope using what's called the Kona Scope. Everybody got one of these little glass spheres with the bubble on the end. If, pretending that this is inside the Polariscope, you're looking at the stone and you're turning it and you see the light sweep across the stone, look to where that darkness, that brush, reaches the edge of the stone. And where it reaches the edge of the stone, you flip it up and you rock the stone back and forth, and you might get these bright rainbow colors. That's the direction of single refraction in a doubly refractive gemstone. If I take my Kona Scope and I touch it to that area, you actually touch it to the stone, touch it to the area of rainbow colors. It may resolve a figure. Oops. It could give you, sometimes you'll just see these like little rainbow concentric circles. So you know you're close to the optic axis, the direction of single refraction. While holding it there, you may see one brush. This means the stone is biaxial. Biaxial stones actually have two directions of single refraction in a doubly refractive stone. You may get an X. This means the stone is uniaxial. It has one direction of single refraction, which is typical in quartz, tourmaline, corundum, and beryl. Or if you have quartz, you'll get what's called a bullseye. And a bullseye means that the X doesn't meet in the center. Often there's a bright green circle or a bright red circle. That is proof that you are looking at quartz. So it's a really fun thing to do. Hunt and find your interference figures or your optic figures. So again, turn your stone, look to see where the brush reaches at the edge of the stone, flip it up, and touch your Kona Scope to it. So remember, every gemstone has one direction of single refraction. So if you've put your stone in and the direction of single refraction is right through the bottom of the stone, it's not going to give you the correct reaction. If it's a doubly refractive stone, it will just look like a singly refractive stone. That's why it's important to flip your stone onto the pavilion of the stone and also turn it in a different direction, so that if it is a doubly refractive stone, you know for sure that if you've tried it in this direction and the table down direction, or even flipping it straight up on its side, just try it in a direction different than table down, you may get a reaction that you didn't see originally. Last piece of advice, red stones lie. A lot of red stones have a lot of strain in them, and you put them under the Polariscope and they give you this hazy fuzziness. We call it tabby extinction. So if your stone is looking hazy and fuzzy, it's a fake reaction. It's common in a lot of the garnets. You'll also see it in actually in blue synthetic spinel. But rubies often have a feature called repeated twinning, where you'll see lines going through the stone, rainbow lines that looks like a fake reaction. So between the garnets and the rubies, we tend to get these two really fake reactions called AEE, anomalous extinction, or over in North America, they call it ADR, anomalous double refraction. So you do need to reconfirm your results on red stones using another piece of equipment. So that's it. That's your Polariscope lesson. Thanks for watching. Bye.